Usually, when we talk about cybersecurity defense, there's this expectation of like rigid architecture.
Yeah.
It's kind of like building a medieval fortress.
Right.
You set up the firewalls, you lock down the ports, and you can basically point to the perimeter and just say, there it is, the walls are up, we're secure.
Well, it's a very binary way of thinking. Like, you either have access or you don't. The system is deterministic.
Exactly. But then you step into the world of artificial intelligence, and suddenly that stone fortress just turns into a cloud of gas.
Mm-hmm.
I mean, imagine this. A Chinese state-sponsored threat actor doesn't just, probe your perimeter.
No, they don't.
Instead, they use an AI agent to autonomously execute reconnaissance, harvest credentials, and exfiltrate data across roughly 30 different organizations all to attack Anthropic's Claude. And because the AI is operating at machine speed, they compress what would be a multi-day cyber campaign into just a few hours.
I mean, that September 2025 attack completely reframed how we have to look at defense. You can't just slap a padlock on a neural network.
You really can't.
It's the absolute definition of an invisible dynamic attack surface.
So true. And hey, welcome to today's deep dive. If you're prepping for your CompTIA SecAI Plus certification, specifically Section 27, which covers AI risks and AI risk responsibility, this is exactly what you need to know.
Yep. Consider this your ultimate shortcut to leveling up.
For sure. We're pulling from a massive stack of sources today. We've got the official CompTIA exam objectives, the OOPS top 10 for large language models, MITRE Atlas, NIST frameworks, and some pretty wild real-world case studies.
A lot of ground to cover.
It is. So let's unpack this new threat landscape. Before we can defend an AI system, we have to understand how fundamentally different it is. Like we said, traditional software is deterministic. Input A always equals output B.
Right, and AI is probabilistic. It's calculating the most likely appropriate response based on just vast amounts of data. And that probabilistic nature is really what breaks traditional threat modeling.
Makes sense.
If we look at the NIST definition of AI risks, it goes way beyond IT. NIST actually categorizes AI harm into 3 distinct buckets.
Okay, what are they?
So there's harm to people, which covers civil liberties and physical safety. Then there's harm to organizations, meaning severe reputational or, financial damage. And finally, harm to entire ecosystems.
Wow, ecosystems.
Yeah.
Like nature.
More like manipulating the global financial system or a national supply chain, big picture stuff.
Ah, got it. And the risk scales up massively when we give these models autonomy to actually act on those probabilities.
Mm-hmm.
In our notes, there are these 2 concepts, excessive agency and action amplification.
Yeah, let's break those down. Action amplification is a major concern with autonomous systems. In traditional software, a single user input usually triggers, like a single bounded function call.
Right.
But an AI agent can take one simple prompt or, one compromised input from an attacker and translate it into a massive automated sequence of API calls, web scraping, and database queries. It just amplifies the action.
It kind of makes me think of giving a highly intelligent but incredibly naive intern a corporate credit card with no spending limit.
That's a great analogy.
Like, they might just keep buying things endlessly to solve whatever problem you gave them.
Exactly. And when you give that intern more permissions than they actually need to do their job, well, you have excessive agency. That naivete is exactly what adversaries exploit, which leads right into the risk of shadow IT and shadow AI.
Right, because developers are moving fast. They want the newest tools, so they just download unvetted open-weight models from the internet, or they use standard vendor tools that suddenly have these hidden AI-based features turned on by default.
And the trap here is that you inherit the vulnerabilities of a supply chain that completely lacks transparency.
Yeah.
Like, if a developer downloads an open-weight model that has a hidden backdoor baked into its training, it's not like traditional software. You can't just push a quick central security patch to fix the weights and biases of a neural network.
No, you really can't.
Once those models are released, they'll live on the internet forever.
So if the landscape is this fast and moving at machine speed, how do adversaries actually break these systems? Let's move from the environment to, active attacks directly on the models themselves. We really have to talk about accuracy and performance.
Yeah. The 2 primary active attacks you'll see here are poisoning and evasion.
Okay.
Poisoning happens early on at training time. The attacker injects falsified samples into the training data to fundamentally infect the model's logic before it even launches.
Oh, wow.
And evasion happens later, at test or runtime. This is where the attacker crafts slightly altered inputs, maybe adding invisible static to an image, just to deceive an already trained model.
And the numbers in the research are honestly stark. One study showed a data poisoning attack dropped an image classifier's accuracy by 27.2%. And that was just trying to tell cats from dogs.
Yeah, pretty significant.
But far more critically, the same poisoning technique dropped an insurance fraud detection model's accuracy by almost 23%.
And what's really challenging is that a model's performance can drop without any active attacker at all.
Wait, really?
Yeah, it's known as model drift. The model assumes the world is static, but reality changes.
Oh, like the classic example from our source is the 2017 fidget spinner craze.
Yes, exactly.
An e-commerce search engine model degraded rapidly because it suddenly encountered a massive volume of queries for a completely unfamiliar term. The real-world environment changed, and the model drifted away from being accurate.
Precisely. But accuracy is really only half the battle here. We also have to look at intellectual property risks. Attackers aren't just trying to break the model, they're trying to steal from it.
Yeah, let's talk about how that actually works under the hood. There's model inversion, right?
Right.
Where an attacker repeatedly queries an AI API, measuring the confidence scores coming back, and essentially uses that math to reverse engineer and regenerate the actual training data. It's kind of like asking a chef 1,000 slightly different questions about a soup until you figure out the exact secret recipe.
That is a perfect way to visualize it. And then there's prompt extraction, which is attempting to trick a large language model, or LLM, into divulging its hidden system instructions. The actual rules the developers wrote to govern its behavior.
And sometimes the users just hand over the IP themselves. I mean, we have cases like the Samsung employees who used ChatGPT to debug proprietary source code.
Oh, yeah, that was a big one.
They pasted highly confidential code into a public model just to find a bug. The LLM retains that session data, meaning that confidential company IP was accidentally leaked to OpenAI, and it could potentially surface in future model training.
Which raises the core challenge of AI security. How do we monitor the invisible? And this leads us directly into passive failures and the human element. Sometimes the system just defeats itself because of the data we feed it.
Let's get into the introduction of bias then. There's a fascinating Stanford excerpt in our stack that points out reality itself is often biased before data is even collected.
Yeah, there are three main types highlighted in the research: systemic, computational, and human cognitive bias. We see real-world failures across the board. For example, there was a healthcare algorithm that prioritized white patients over black patients with similar medical needs.
Okay, I have to pause here. If an algorithm is just looking at numbers, how does math get biased?
Well, the math doesn't exist in a vacuum. In that healthcare example, the algorithm used historical healthcare spending as a proxy for health needs. Because historically underserved populations had less recorded medical spending due to systemic inequalities, the algorithm wrongly assumed they were, quote-unquote, healthier and deprioritized them. Algorithms act as a feedback loop. They formalize and amplify historical human biases because they optimize for the patterns they see in flawed data.
So the math is literally just doing its job, but it's learning from a fundamentally flawed textbook.
Exactly.
And speaking of data behaving badly, we have to talk about accidental data leakage, specifically with retrieval augmented generation pipelines.
RAG is incredibly popular because it lets you connect a smart LLM brain to your company's private database. But the access control risk is immense.
Yeah, there's a scenario in our notes where an AI chatbot leaks proprietary HR documents to a user, literally pulling salary information from a completely different user session from the day before.
An absolute nightmare for compliance. And that ties directly into reputational loss. Look at OWASP scenario number 2. A company deploys a medical diagnosis chatbot. It hallucinates poor information, leading to patient harm and massive lawsuits.
What really stands out to me about that scenario is that a safety breakdown here does not require a malicious attacker. Like, hallucinations alone can destroy a brand. The AI just confidently making things up is enough to get you sued.
Which brings us to the most important part of our deep dive: taking back control. I mean, how do we actually govern probabilistic systems?
Right. We looked at responsible AI and awareness training.
The NIST AI Risk Management Framework, or AI-RMF, is basically the gold standard here. It emphasizes continuous validation. You can't just test an AI once and deploy it. You need structured evals.
Evals.
Yeah, think of evals as automated grading rubrics that constantly measure the AI's output quality against human-defined criteria.
Got it. And you need circuit breakers too, right? Automated systems that pause high-risk capabilities,
Right.
like an AI agent trying to send an outbound email, if certain behavioral thresholds are crossed.
Automation is critical, yeah, but it isn't enough. You must have awareness training and a human-in-the-loop operational design. High-risk AI just cannot run unchecked. There is a massive AI security skills gap right now because traditional software training just doesn't apply to probabilistic systems.
It's exactly why the CompTIA SecAI Plus certification exists. You need human supervisors.
It kind of makes me think of the old coal mines. We need to deploy daily canaries, sending known good and bad examples to the model every day to test its behavior, just making sure the data error isn't toxic before the model breaks it in. The paradigm shift here really is moving from deterministic defense to probabilistic defense.
All right, listener. You have survived the conceptual deep dive.
Oh,
Now it is time to put that knowledge to the test.
here we go.
Welcome to the Ultimate SecAI Plus Audio Exam Simulator. We're going to run through a rapid-fire quiz covering 40 questions from our source stack. I'll pose the questions to you, the listener. See if you can answer them in your head. Our expert here will reveal the correct answer and give us the quick why behind it.
Sounds good.
For the performance-based questions, the PBQs, I'll frame them as a scenario challenge for you to mentally configure. Let's do this.
I'm ready. Let's start the clock.
All right, we'll kick things off with Focus Area 1, Responsible AI. Listener, question 1. Which framework is explicitly designed to help organizations manage AI risks across its life cycle?
That would be the NIST AI RMF. It's the foundational governance standard for mapping and managing risk.
Right. Question 2. What is the term for a structured mechanism that measures AI output quality against human-defined criteria?
Those are called evals. They act as that continuous grading rubric we discussed.
Awesome. Question 3. What operational design requires a person to review and approve AI actions before they're executed?
Human in the loop. It is an essential safeguard for any high-risk autonomous task.
Nice. Question 4, our first PBQ scenario challenge. You are deploying a high-risk AI tool. Mentally drag and drop the correct sequence of these 3 safety checks. Deploy to prod, bias audit, and adversarial red teaming. What goes where?
Okay, the correct sequence is bias audit first, followed by adversarial red teaming, and finally, deploy to prod. You audit for fairness, then attack it to test robustness, and only then do you deploy.
Spot on. Moving right into Focus Area 2, AI risks. Listener, question 1. NIST defines AI harm in 3 broad categories. Harm to people, harm to organizations, and harm to what else?
Harm to ecosystems. This looks at broad systemic impacts like disrupting the global financial system or supply chains.
Yep. Question 2. Which framework specifically tracks adversarial tactics and techniques against AI systems?
MITRE ATLAS. Similar to MITRE AT&CK for traditional networks, ATLAS maps the threat landscape specifically for AI.
Question 3. What specific risk occurs when an AI model assumes things will continue as they historically have, blinding it to sudden innovations?
That's stability bias. The model essentially discounts the possibility of significant sudden change.
And question 4, PBQ scenario. An attacker uses a generative AI to create deepfake phishing audio. Categorize this threat using the AI risk repository.
This falls under human or intentional post-deployment misuse, specifically the cybercrime category.
All right, 2 sections down. Let's tackle Focus Area 3, Introduction to Bias. Question 1. What type of bias occurs when training data is not representative of the overall population, like a facial recognition system trained mostly on lighter skin tones?
Sampling bias. The data sample simply didn't represent reality accurately.
Question 2. What bias is introduced when a developer's own preconceptions influence the model design?
Confirmation bias. The developer is unintentionally reinforcing their own assumptions in the model's architecture.
Right. Question 3. When an algorithm optimizes for accuracy alone and completely overlooks fairness constraints, what kind of bias is this?
Algorithmic bias. The math is just prioritizing the wrong overall goal.
Question 4, PBQ scenario. Your healthcare allocation AI is prioritizing white patients over black patients. Identify the root cause and the immediate mitigation step.
Well, the root cause is societal or historical data bias, and the immediate mitigation is dataset rebalancing and applying fairness-aware algorithms to correct the skewed feedback loop.
Take a breath, listener. You're doing great. Focus Area 4, Accidental Data Leakage. Question 1. What popular enterprise AI architecture carries a high risk of leaking proprietary corporate documents if access controls aren't strictly enforced?
That's Retrieval Augmented Generation, or RAG. Connecting an LLM to private databases is super risky without strict permissions.
Good to know. Question 2. What type of attack infers whether a specific individual's data was part of a model's training set?
A membership inference attack. It's a massive privacy risk for sensitive datasets.
Question 3. When an AI model memorizes and inadvertently spits out a user's PII, their personally identifiable information, what OWASP pick vulnerability is this?
Sensitive information disclosure.
And question 4, PBQ scenario. You are configuring a RAGA pipeline for HR. How do you prevent user A from querying user B's salary?
You absolutely must implement role-based access control, or RBAC, directly on the vector database or knowledge store. The LLM shouldn't even be able to see data the user doesn't have permissions for.
Halfway there, let's look at Focus Area 5, reputational loss. Question 1. Does an AI system need to be actively hacked to cause reputational and financial damage to a company?
No, it doesn't. Unintentional hallucinations alone can cause massive liability, just like we saw with the medical chatbot.
Question 2. If an AI chatbot provides dangerous medical advice, which OWASP category does this fall under?
That is LLM09, misinformation.
Question 3. What mitigates reputational loss from an AI producing offensive content?
Content filters and guardrails. You need automated checks on both the input prompts and the output responses.
Question 4, PBQ scenario. Your company's customer service AI starts hallucinating fake refund policies. Design an automated response to protect the brand.
You'd implement a circuit breaker to automatically pause the AI's capability to respond and immediately route the active chat to a human agent.
Smooth save on the brand reputation. Focus Area 6, accuracy and performance of the model. Question 1. What phenomenon occurs when a model loses predictive power because the real-world environment has changed since it was trained?
Model drift. Remember the sudden 2017 fidget spinner craze?
Always. Question 2. In the context of machine learning performance, what metric represents the harmonic mean of precision and recall?
The F1 score. A score of 1 indicates perfect precision and recall.
Question 3. What type of attack happens at test time to mislead testing data and lower accuracy?
An evasion attack, where inputs are slightly altered to trick the model.
Question 4. PBQ scenario. An attacker injects falsified samples into your training data, dropping your model's F1 score by 0.34. Identify the attack type and the defense.
The attack is data poisoning. The defense requires rigorous data quality audits and continuous validation during the training phase.
Excellent. Focus Area 7, intellectual property risks. Question 1. What attack involves querying an AI to replicate its behavior and steal the underlying model?
That's a model inversion attack.
Question 2. What attack attempts to trick an LLM into divulging its hidden system instructions?
Prompt extraction.
Question 3. Digital files containing a model's weights and biases are primary targets for what threat?
Model theft, because if they steal the weights, they steal the brain.
True. Question 4, PBQ scenario. An employee wants to use ChatGPT to debug proprietary source code. Establish a policy to prevent IP loss, like the Samsung incident.
You need to block public LLM usage for proprietary code entirely and deploy an internal, locally hosted, isolated model for developers to use instead.
Getting into the home stretch. Focus Area 8, autonomous systems. Question 1. When an AI agent translates one prompt into a long sequence of API calls, what risk is amplified?
Action amplification. A small input turns into a massive chain of events.
Question 2. What OWASP vulnerability occurs when an AI agent is granted more permissions than it needs to function?
Excessive agency.
Question 3. How do autonomous AI attacks differ from human hackers regarding speed?
Well, they operate at machine speed without fatigue, compressing what used to be multi-day attacks into mere hours.
Question 4, PBQ scenario. Your AI agent needs to read a database to answer customer queries. Currently, it authenticates with full administrative database privileges. Remediate this setup.
Apply the principle of least privilege. You should issue the agent a read-only OAuth token so it can view the data but cannot modify or delete it.
Love it. Focus Area 9, Shadow IT and Shadow AI. Question 1. What is the primary danger of employees using unvetted open-weight models downloaded from the internet?
They might contain hidden backdoors and they cannot be centrally tracked or easily patched like traditional software.
Question 2. Why are AI-based features in standard vendor tools considered a shadow AI risk?
Because developers often enable them by default without really understanding how to secure or dynamically test the underlying generative model.
Question 3. What happens when AI agents act as a medium of reconnaissance inside a corporate network?
Cyber espionage. They end up exposing internal metadata and access patterns to unauthorized users.
Question 4, PBQ scenario. You discover multiple departments using unauthorized SaaS AI tools. Design a technical control to manage this.
Implement an AI agent gateway to route, authenticate, and monitor all outbound AI traffic through a single choke point.
Final stretch, listener. Focus Area 10, awareness training. Question 1. What is the core goal of the CompTIA SecAI Plus certification?
To close the AI security skills gap by validating knowledge in securing and governing these specific systems.
Question 2. Why is traditional software training insufficient for AI security?
Because AI logic is probabilistic and dynamic, whereas traditional software is static and deterministic, the old rules just don't fully apply.
Right. Question 3. What is the recommended first step to move a team out of ad hoc experimentation into secure ML maturity?
Implement source control for notebooks and use lightweight experiment trackers to log what models are actually doing.
And question 4, our final PBQ scenario. Build an awareness training loop for human reviewers handling AI outputs. What 3 metrics must they track?
They must track quality control and error rates, time efficiency, and the cost impact of the AI's decisions.
Wow. Take a breath. I mean, if you mentally nailed those scenarios and concepts, you are in phenomenal shape. Congratulations on surviving the ultimate deep dive in exam simulator.
Yeah, it's a super dense topic, but a vital one. We wish you the absolute best of luck on your CompTIA SecAI Plus journey.
Definitely. We started today by talking about how traditional security is like a stone fortress, but AI security is like trying to lock down a cloud of gas. As you head out into the field to secure these probabilistic thinking systems, remember that the gas isn't impossible to contain. You just need a completely new set of tools to measure the air. It leaves us with a pretty wild thought. As AI increasingly defends against AI, human cybersecurity professionals are going to transition from being operators who configure firewalls to being the final human-in-the-loop supervisors of a machine-speed cyber war. Think about that as you prep for the exam. Stay curious, stay secure, and we will catch you on the next deep dive.